Hello students, and welcome to the 56th lecture on particle physics, and this will be the last 5 lectures where we will be discussing about the kinematics of the reaction, the various features of accelerators, linear accelerators, synchrotrons, colliders, etc. Then the detectors like bubble chambers, cloud chambers, GM counter, Cherenkov detector, etc. But first, before we talk about accelerators and detectors, let us start with simple kinematics to understand the fact that suppose we are talking about cross section of a reaction where, say, electron-proton scattering is happening. Now, if I consider a particular center of mass energy, then the value of the cross section, whether I am doing the experiment in laboratory frame or I am doing the experiment in center of mass frame, that would be unique. That will be common. Okay, that number will be the same whether we perform the experiment in center of mass frame or we perform the experiment in laboratory frame. Then whether that experiment has been performed in India or somewhere else in the world like Australia, CERN, Fermilab, anywhere, if we are doing electron-proton scattering, if that has the same center of mass energy, the events will be the same. The cross section will be the same. The probability of interaction will be the same. And whether we perform that experiment today or after 1 year or after 10 years, the probability of interaction will be the same. Now suppose someone has performed the experiment in India in laboratory frame and another guy has performed the experiment in center of mass frame. And what I am telling you, that features will be the same, the observations will be the same, the end result will be the same. This means that there must exist a transformation between the laboratory frame of reference and center of mass frame of reference. Because the important point is that if, for example, if I have got an electron beam of 500 MeV and I have got a proton target and the target is at rest, that means we are talking about laboratory frame of reference. Now, if we are talking about an electron beam which is coming and the proton target which is at rest, then the scattering that will happen and the results that I will note down. If somebody is in United States and he wants to repeat the same experiment in center of mass frame, then my observations for that given center of mass energy should also tell him that what was the scattering angle. That means the scattering, the detector where I have placed, suppose this is the lab frame where electron is coming and I have placed a detector as say 30 degrees. Now, if someone is doing the experiment in center of mass frame, he has kept center of mass energy to be what we have done, but at the same time, at a particular angle, with the events which we have observed, say at 30 degrees where we have placed the detector, at what angle he should keep the detector to observe the same event. And that means there must be a transformation between the lab angle and the center of mass angle, lab energy and center of mass energy, and all that. And this is what will be the topic of discussion in the next 3 lectures. And then we will qualitatively discuss about in one lecture about the accelerators, features of accelerators, and the detectors. Those are being widely used in particle physics experiments. Therefore, let us start with the plan of the next 4-5 lectures are that first we will talk about relativistic kinematics, Mandesta variable, Lorentz transformation, transformation of velocities, Lorentz transformation for energy and momentum, transformation of the scattering angle, and that is how we can go from lab frame to center of mass frame or vice versa. Then you can apply this formula to any other frame. Then particle accelerators, main features of cyclotron, linear accelerators, colliders, storage ring, synchrotrons, and then finally particle detectors, cloud chamber, bubble chamber, Geiger-Müller counter, scintillation detectors, Cherenkov detectors, and calorimeters. Therefore, let us start with a very simple case. Let us talk about laboratory frame of reference. Now, in laboratory frame, what happens? We know that there are two guys, 1 and 2. Scattering takes place, and we have in the final state two guys, 3 and 4. Now, for elastic scattering, we have electron proton here, electron proton here. For inelastic scattering, we can have, say, instead of 3 and 4, we can have something else also. We have electron, neutron, and a pi plus, or we can have pi minus plus p going to pi 0 plus n. Now, what I am telling you that this is my target, this is the projectile, therefore this is the target, this is my projectile. Say the projectile I am writing it as 1, target I am writing it as 2, and target is at rest. And then scattering is taking place. We have 3 going at an outgoing angle of theta, which I am calling it as theta lab, because I am going to place my detector at this place to detect particle 3. And then say the particle 4 is recoiling somewhere at an angle phi from the original direction of the beam. Therefore, this is 1 is my beam and 2 is my target, and target is at rest. Therefore, the important point is that the projectile has got certain energy, E1, it has got certain momentum, P1, while the target is at rest. Its energy is just its rest mass energy in units of C and H cross. That means the natural units, otherwise it will be M2C square, and it is at rest. Now, the important point is that if we are observing particle 3 at a certain angle theta, then there is no need to observe particle 4, because by applying energy momentum conservation, we will be able to tell the energy of the particle 4, and even also we will be able to tell if 3 has come out at an angle theta lab, then at what angle the guy 4 has come out. What was the angle between the beam direction and the direction at which particle 4 has recoiled. Therefore, the important concept is that if I know, for example, theta lab, I know the energy of the incident particle, I know only these two guys, E1 and theta lab, then I will be able to tell E3. Not only E3, I will also be able to tell what will be its momentum. And not only that, we will be also able to tell this angle phi if I know E1 and theta, and E4 and P4. Therefore, the important point is, and this we have discussed while talking about the neutrinos and the detection of muons in the final state. What I had told you, that we observe muon energy and at what angle those muons are coming, and from there we infer that at what was the energy of the incoming neutrino, because in neutrino we cannot see. But here the examples which I have taken, I am talking about electron, pions, etc. They are coming with certain energy and momentum. Therefore, we have E1 theta lab. E1 is the energy of the projectile. Theta lab is the lab scattering angle. And then a scattering is taking place. And we are looking at the events which are coming at theta lab. And from there we are inferring what will be its energy, E3, what will be its momentum, P3, and then what is this angle phi, and then the energy of the particle 4 and the momentum of the particle 4. Therefore, we need only two quantities like this, or we need E1, E3 only, or we need like E3 theta lab also. If we are given E3 and theta lab, like in the case of neutrinos, we were in the interaction like mu plus n, mu minus plus p, we were knowing the muon energy and the scattering angle, and then from there we were able to infer what was the energy of the neutrino. Therefore, if we know E3 theta lab, we will be able to know E1, we will be able to know P3, phi, E4, P4. Or in other words, you can say that if I know E1 and E4, then I will be able to tell what was phi, what was theta lab, what was E3 and all that. That means instead of putting detector to detect particle 3, if I am putting a detector to detect particle 4, then I will be able to say that, okay, I am measuring the energy of the particle 4. That means I am talking about energy distribution, and I know the energy of the incident projectile. Then I will be able to tell the energy of the particle 3, at what angle this particle 4 has come out, at what angle theta this particle 3 has come out, and all that. And not only this, the topic is interesting because this is about lab frame, and I am telling you that only two quantities are, that means linearly independent, and that depends upon you what you are opting for, E1 theta lab or E1 E3 or E1 E4 or E3 theta or whatever you like. And then you are describing completely about the other fellow. Now the other important catch is what I am telling you. Suppose I perform this experiment in India and then somebody wants to repeat this experiment, but he can do only the experiment in center of mass frame. Then at what angle he should place this detector? What should be the equivalent angle for him to see the same event? And what, because in the center of mass frame, now here in the lab frame, one guy was at rest and another fellow was coming with certain energy and momentum. Now here both the guys will come with the same magnitude of momentum but only opposite in direction. Electron is here, proton is here. These two guys are coming together to collide or to interact, and such that scattering will take place, and the magnitude of the momentum of these two guys are the same, only the directions are opposite. One is electron and another is proton. Since magnitudes are same, then the energy for these two will be different. Let us call it by the name E1 and E2, but magnitude of the momentum will be the same. And then what I am telling you, that in the final state we have 3 and 4. Then at what angle I should place the detector to observe the same event as what we have observed in India in the experiment performed using target at rest and all the energy that was provided to the projectile. And that means what I am telling you, that if I know E1 and theta lab, then I know E3, I know phi, I know E4, momenta, and then what I am telling you, that this will also give me the center of mass energy, which is represented by square root S. This we call it by the name center of mass energy. That means if say this S for 1 plus 2 in the initial state going to 3 plus 4 in the final state, this S, though we have already introduced it in the previous classes, is P1 plus P2 whole square, sum of the 4 momentum square. And that will be from momentum conservation, since in any interaction, momentum and 3 momentum and energy both are conserved, then that means P1 plus P2 must be equal to P3 plus P4. And that means S is equal to P1 plus P2 whole square. That means this is equal to P3 plus P4 square. And what you are going to observe from here, that this S will be equal to P1 square plus P2 square plus 2P1 dot P2. And that means this S will be equal to M1 square plus M2 square plus 2. Now this P1 is the 4 momenta, therefore it will have energy component and it will have the momentum, 3 momentum component. For P2, 2 is at rest, energy will be the equal to momentum, mass of the particle, and 3 momenta will be 0. Therefore, this will be P1 dot P2 will just give me 2M2 E1. And therefore, if I know E1, the laboratory energy, the incident energy of the particle, I will be able to tell what will be my S. And that means what is the center of mass energy? This will be square root of M1 square plus M2 square plus twice M2 E1. Suppose I am talking about 500 MeV of electron. How much would be the center of mass available energy? This will be equal to, let us write it in GeV, that means this is equal to 0.5 GeV. This will be 0.5 square plus roughly 0.938 square plus 2 into, for the proton, 0.938 into 0.5. This will be the center of mass energy. And that means if somebody is talking about electron proton scattering in center of mass frame, then I have to supply him this value. What should be square root S? What should be the total center of mass energy for this system? It is, here we are not talking about what should be the energy of E1 or what should be the energy for the proton, because just we know that when we are talking about the energies, we have to consider, in this case, mass is also important. This is 938 MeV, while here the mass is only 0.5. Sorry, when we are considering to be in GeV, this is, I'm very sorry, this is 0.5 MeV for the mass. This will be 0.5, rather it should be, for electrons mass is 0.5 MeV. Therefore, this will be 0.5 into 10 power minus 3 square, and that will be, square will be 10 power minus 6. Therefore, you will neglect this, and here it will be simply 2 into 0.938 into 0.5, because the energy of the particle is 500 MeV, and that will be the kinetic energy, as we are seeing that the rest mass energy of the electron is very small. Therefore, we are neglecting that and we are considering only the energy of the incident electron. Therefore, in most of the cases, what we are finding out that we have square root S, which is for lab is this quantity, and for electron-proton scattering, then we have to see that magnitude of the momenta for electron and for proton should be the same. Only energy will be different because the masses of electron will not be the same as the mass of the proton. Moreover, you can notice that since electron mass is negligible, therefore most of the time the electron's energy will be the momentum of the electron in units of C and H cross, and here the kinetic energy and momentum will be different. This is what we are going to talk about, and for this we are going to introduce Mandelstam variable. What are these Mandelstam variables? Are a set of 4 variables commonly used in particle physics to describe particle scattering. They are named after the Russian physicist Mandelstam, who introduced them in the 1950s. The 4 Mandelstam variables, usually they are denoted by S, T, U and M, and are defined in terms of the 4 momenta, energy and momentum of the particles involved in the collision. S is the center of mass energy squared that we have discussed. This variable represents the total energy available in the center of mass frame of the collision. In particle collisions or scattering, S is the square of the total energy of the system in the center of mass frame. Therefore, what is this S? As you notice, this was P1 plus P2 whole square, and this will be equal to, in center of mass frame, if I talk about E1 plus E2 whole square in center of mass frame plus minus P1 plus P2 whole square. And now you know that these two are equal in magnitude and opposite in direction. Therefore, that means what I am telling you, that P1 is minus P2, and therefore this guy is going to cancel out and you will have just E1 plus E2 whole square. And that means what is square root S? This is E1 plus E2, the center of mass energy. And that is what I have written here. S is the square of the total energy of the system. That means root S, this is this guy. If you square this, you will have S is equal to E1 plus E2 whole square in center of mass frame. Then comes T. T is the momentum transfer squared. This value represents the square of the momentum transferred between the initial and final states of the scattering. That means if I talk about 1 plus 2 going to 3 plus 4, then this T is P1 minus P3 or P4 minus P2, because again you have to keep this 4 momentum conservation in mind, that 1 plus 2 must be equal to 3 plus 4, and therefore P1 minus P3 must be equal to P4 minus P2 whole square. And this is the 4 momentum transfer. But that means an electron emits a virtual photon and it moves in some direction, and this is absorbed by the incoming proton, and the proton moves in some other direction. This momentum I am talking about P1, this 4 momentum I am talking about P3, this is P2, and this guy is P4. 1 plus 2 going to 3 plus 4. And this virtual photon, because this is not on mass shell, it has got a 4 momentum transfer square, which is not equal to the mass of the photon square. These are not real photons. And therefore, how much is that transfer? That transfer is, we generally write it as Q square, that is equal to P1, this is also T is P1 minus P3 whole square and P4 minus P2 whole square. And this Q square is again P1 minus P3 whole square or P4 minus P2 whole square. Therefore, all S, T and U, those will have 4 momentum components, and those will be in a square. S is P1 plus P2 whole square, and that is equal to P3 plus P4 whole square. T is P1 minus P3 whole square, or equal to, this is equivalent to P4 minus P2 whole square. When we will introduce U, that will be P1 minus P4 whole square, P1 minus P4 whole square, and that will be equal to P3 minus P2 whole square. Therefore, this Q square is P1 minus P3 whole square, or this is equal to P4 minus P2 whole square. And then if I talk about this Q square, which is equal to T, and that is equal to P1 square plus P3 square minus 2P1 dot P3. Now this will be M1 square plus M3 square minus twice, in lap frame this will be, E1 E3 minus P1 dot P3. And what is the angle between 1 and 3? This was the projectile, this was the target. The scattering angle is theta lab. This is my particle 3. And therefore, this P1 dot P3 is nothing but mod of P1 times mod of P3 times the cosine of the angle between 1 and 3. And this is nothing but the lab scattering angle. And therefore, Q square is this guy, M1 square plus M3 square minus twice E1 E3 minus P1 P3 cosine theta lab. Now again I am telling you that if we know E1 and theta lab, we will be able to get E3, and that means we will be able to tell you what is the value of T. Therefore, this is T and is defined as the difference in the squared 4 momenta of the initial and final particles in the scattering. This variable is similar to T, the U's. It involves a different combination of initial and final state momenta. This is what I call it as P1 minus P4 whole square or P3 minus P2 whole square. This is U. U is also defined as the difference in the squared 4 momenta of the initial and final particles. Therefore, this is what we are talking about. S channel, T channel, U channel. You see, this is P1 plus P2 whole square. This is P1 minus P3 we are talking about. And here we are talking about P1 minus P4 or P2 minus P3. Now the important catch, and that we have discussed in the class, that S is P1 plus P2 whole square, T is P1 minus P3 whole square, and U is P1 minus P4 whole square. When we sum them up, S plus T plus U, what we had seen in the class, that this is P1 square plus P2 square plus twice P1 dot P2 plus P1 square plus P3 square minus twice P1 dot P3 plus P1 square plus P4 square minus twice P1 dot P4. And then this P1 square, P1 square, P1 square, 3 places. This will be 3M1 square plus M2 square plus M3 square plus M4 square plus twice P1 is common, P2 minus P3 minus P4. And we know that P1 is P2 plus P3. P1 plus P2 is P3 plus P4. Therefore, P1 is equal to minus P2. Let me write it neatly. P1 is minus P2 plus P3 plus P4. And therefore, when you put it here, what you are going to get is, as you can notice, I can replace this guy by minus P1, and this will be minus 2P1 square. That will be minus twice M1 square, and this is nothing but 3M1 square minus twice M1 square. Okay, and that means M1 square plus M2 square plus M4 square, and that is nothing but what we have written in one of the classes as square root mi square. Therefore, this is what we have STU. M is the invariant mass square. This variable represents the square of the invariant mass of the system. This is what we have talked about in the context of particle collisions. Now, M, it often refers to the squared mass of the intermediate state particles. Okay, M1 square plus M2 square plus M3 square plus M4 square. What if you have more particles? Similarly, you will add them up. Now, up to this point, everything is fine, that we have 1 plus 2 going to 3 plus 4. Now, we are going to understand this more clearly. For example, if I am talking about an elastic scattering, A plus B going to A plus B, and consider that particle A has got a mass which is almost negligible. If we consider a photon, if we consider a neutrino, if we consider an electron, then if the lab energy is say 500 MeV or 800 MeV or 1 GeV, then we are talking about say simply I am taking the lab energy to make life simple, 200 MeV, and that will be 0.2 GeV. Okay, and then mass of the electron is say 0.5 into 10 power minus 3 GeV. Therefore, mass of the electron square will be 0.25 into 10 power minus 6. And that means this is of the order of 2.5 into 10 power minus 7 GeV square. And that is why when we are talking about E lab to be 200 MeV, since we see that these comes in squares, therefore we do not include the masses of these particles. Okay, but why we are doing it? Suppose I have Q square, which was T. This was P1 minus P3 whole square, and this we found out that this is equivalent to P1 square plus P3 square minus 2P1 dot P3, and this we saw that M1 square, we are not considering it, we are taking M1 square. Let me first write it, M1 square plus M3 square minus twice E1 E3 minus P1 P3 cos theta lab. Now what I am telling you, that M1 is small such that my E1 is in natural units is of the order of P1, or E3 is of the order of P3. Then this is approximately, we can write it as minus twice E1 E3 1 minus cosine theta lab. Okay, if you include the mass of the particle, then you have to use square root of that, and this we have discussed already in one of the classes. Therefore, this is Q square. Now, the other point is, since P1 plus P2 is P3 plus P4, we also saw that Q is nothing but P4 minus P2. That means P4 is P2 plus Q. We are talking about elastic scattering. Therefore, P4 square is P2 square plus Q square plus twice P2 dot Q. And for elastic scattering, P4 square is the same as P2 square, and Q square is equal to minus twice P20 Q0 minus P2 dot Q. Since 2 is at rest in laboratory frame, therefore this will be 0, and what will be Q0? This will be the energy transferred to the target particle. Therefore, we saw that energy of the incoming electron was E1, outgoing electron was E3. Therefore, this we will write it as P20 is the rest mass energy of the particle. This will be the mass of the particle. Let us write it by M, and then this is E1 minus E3. And when we compare these two, because here also we have q square, here also we have q square, what we realize that -2 will cancel out. You have m E1 minus E3. This is simply E1 E3 1 minus cosine theta lambda. And from here, you can write E3 in terms of E1 and theta lambda. Therefore, this we have done in the class, that we can write E3 in terms of E1 and theta lambda. Therefore, what you are realizing that if I know E1 and theta lambda, I will be able to tell you what will be E3, energy of the particle 3. And then what is important, that equivalently I should also be able to tell what will be the equivalent center of mass energy, and that was simply S is equal to P1 plus P2 whole square, and then we have to take square root of S to obtain the equivalent energy in the center of mass frame. Therefore, we will continue the discussion on this regarding the lap frame and the center of mass frame, and how the transformations we can understand from one frame to another frame. Let us stop here. Thank you very much.